All right, Dinesh, we're going to give it another like 30 seconds. There's people trickling in from the poster session.
No problem. I totally understand.
All right, everyone, welcome back. I hope you had a good poster session, had some productive talks, learned some new things. This next talk is going to be from Dinesh Manocha from, from University of Maryland at College Park. The talk title is going to be Robot Navigation in Complex Indoor and Outdoor Environments. Dinesh is a Paul Krisman Uribe Professor and a Distinguished University Professor of Computer Science and Electrical and Computer Engineering at the University of Maryland College Park. He's published more than 800 papers and supervised more than 56 PhD dissertations. He's an inventor of 17 patents, some of which licensed to industry. His group has developed many widely used software systems with 2 million plus downloads and licensed them to more than 60 commercial vendors. He's a fellow of AAAI, AAAS, ACM, IEEE, NAI, Washington Academy of Sciences, a member of ACM, SIGGRAPH, and IEEE VR Academies, and a recipient of the Bezier Award and Jimmy H.C. Lin Award. He received the Distinguished Alumni Award from IIT Delhi. He has co-founded multiple companies, including Impulsonic, which was acquired by Valve. So this is Dinesh Manocha. Go ahead, take it away.
Thank you. Good morning. Can you hear me well?
Yes.
Great. Thank you for your kind introduction. And let me first of all thank the organizers for the wonderful workshop. And it's my big loss that I'm not there in person. I've been hearing some really two good talks in the morning. So really honored to be here among all these wonderful speakers talking about all the challenging issues of outdoor autonomy. So I'll talk about the work my group has been doing at Maryland, especially on robot navigation, complex indoor-outdoor scenes. I just want to acknowledge a lot of my current and former students. Some of you have graduated. And I also want to acknowledge three external collaboration, Army Research Labs, Google, as well as Amazon. So I have wonderful collaboration with all these different folks at organizations. So, if you're talking about robot navigation, this is 2025, and everybody's saying now they came to the conference using Waymo, right? So that's a great example of Waymo's almost autonomous, a little bit remote watching, but that's a great example of, a robot navigating on the streets of San Francisco or LA. And of course, there are also people working on off-road autonomy, which is a very hot problem right now in Department of Defense and other kind of agriculture applications. So the end goal is that if my robot goes to any place, let's say if I come to USC campus for the first time, I figure my way around how to walk on the sidewalk, avoid bad areas, go to the building, inside, outside. So the question is, we want that if you're given a robot, and robot may or may not have a map or a course map, some kind of information, just like humans figure their way out, we want robot the same technology. So we ultimately do it. And of course, if robots are next to human environment, it's indoor scenes, we want robot to follow all the norm, which is a field called social navigation. So this is really not an old problem. I myself involved in motion planning for 30 years, and I can, if I start serving literature, about 50 years of literature, and there's a lot of work done, including some talks this morning. So I will just jump to some of the work we have done and the challenges we still have. This is. But where do things today? There are things working. For example, I would say, do you see autonomous robots or semi-autonomous robots, but still in somewhat controlled environments? And what does control mean, So the classic example is Amazon warehouses, where they have been deploying robots for transportation, material transportation, other factories. But they designed these warehouses to be robot friendly. What sensors they put, what humans do and do not allow. So in a way, they make the environment easier so that really it's friendly for robots. And you can also put the sensor and lighting. So that's where people have done quite a good job comes up here. I want to mention to you one of the projects we were working on with Amazon, Lab 126. They introduced a consumer robot into about 3 years ago. And the challenge was to make consumer robot in the home. And I told my friends at Amazon, you guys are crazy. Home is one of the most hardest place because Everybody's home is different. In my home, I make mess, and as my wife will tell you, I make different mess at different time, right? And she has to put up with it. So robots hard. And the third thing in home robot is like this is a robot. I showed the video of Amazon has Astro robot here. So this is like a $1,500 robot. Should be working in everybody's home. So the companion here, you can see the form factor, and they can map it, and you should walk around you, automatically go around, play with you, make sure it doesn't hurt a kid, doesn't hurt everybody. You can remote monitoring. This is a classic example of, why home robots is hard, because they're worried about the cost factor, $1,500. So they could not put a LiDAR. LiDAR more expensive, and LiDAR don't rely. And secondly, you put sensors like camera. We're asking about we hear about LiDAR, radar, they're great sensing, but you have very little compute. They can't even give you a dedicated GPU instead of ASIC chip. So the sensing costs and the reliability and the limited compute, edge computing, so you don't have a big GPU, just makes this problem much harder. That's what a problem robots have to do. So not only we need the machine learning or AI to do the environment and understanding, but we have to make sure anything we design should work on the edge computing. Like I just saw an announcement, this morning that Google Gemini Robotics have introduced a version which runs on low-end platform. So that's a really step in the right direction. So where do things happen? So there have been many projects. A few years ago, Amazon was doing delivery project, Scout. They actually called it off. Amazon spent, God knows, tens of billions of dollars on delivery. And they say, won't it be nice, instead of a doorman, somebody dropping a package in front of your door outside your apartment, a robot comes and you pick it up. This was the thing they started, and they called it off, whatever reasons they have. But this was a nice street they were doing it. Some of the work I've been doing, I have my former students in Hong Kong and other places, or you go to Asia, right? I'm originally myself from India. You got very challenging environments. So you suddenly see this here, like here's one of a robot with sensing, walking in the streets of, let's say, Hong Kong, other parts of it. So you see robot limited sensing, and there are a lot of human crowded environments, houses here. So look at the difference between what I call on the left, a nice, clean, open street, versus robots operating in very crowded scenes right here. So this is where the challenge comes up, we still have a long way to go. How do we do it? And as you talk about robot navigation, I guess one of the biggest success stories just is Google Waymo, right? And this is a week on 2 days ago, Tesla announced robot taxis in Austin. They're testing with a human driver. Waymo just expanded to Atlanta in Uber. So it's really taking off, Now, this is an amazing success story that this is a slightly old video of Waymo. And I'm sure if you're in LA, you can take Waymo rides. In San Francisco, you can take Waymo rides. In Austin and Phoenix, you can do it. So this is a place where they really have spent for 15 years, spent, God knows, tens of millions of miles of data, really mapped the environment well, and still they're going slowly. Only few parts of LA, few parts of West are converted. So even if where we are, they're really coming out well. But let me give you an example. 60% of the world population live in Asia. And many years ago, I was involved with the project of collecting Asian driving data. So this is a data set we released a few years ago. It was published. It's a Meteor. And this is what I call, compare the driving on the left to driving on the right. You got all kinds of behavior. You got very congested traffic, and you don't have people who follow rules. So, if human drivers on the road don't follow rules, how are the autonomous cars going to do? One of the lot of accidents happen because of human drivers have errors. So this is the kind of situation we're doing it like, okay, now you come here, you've got two-wheelers, you've got no lanes, you can see crazy traffic. So the question is, when can we have autonomous robots or physical AI working in this kind of environment? So we still have a very long way to go, what I call complexity. And of course, Waymo has been a role. Just in the last 1 year, they went from 50,000 rides to 250,000 rides a week, 1 million miles. As I said, they're doing it well. They heavily map. I think in some ways a great success of physical AI and autonomy, what Waymo has achieved. We really applaud them. But keep in mind, they're not 100% autonomous. I heard they remotely watch and one human watching N cars. I don't know the details, how often they interfere, but there's somebody watching over you. And this thing is still cheaper that if one can do N, and as it increases, the human cost goes down there. And as I said, there are a lot of traffic situations. There's another Asian traffic situation on the left. So look at the traffic condition on the left and right, So this is, again, a lot of population lives in this environment. So, it takes a long time. Even the best of human drivers struggle. So when can autonomy really work in this environment? So just if you want to work in this area, we did a lot of work. We captured a lot of data set from India, Meteor. You're welcome to download and play with it. People are using it and testing the new perception and planning methods here. One thing in the Meteor was that we have different behaviors, like different kind of behavior, if you can read on the left, overtaking, overcoming, vivid, and also different agents from like bicycle, ego vehicle, even like a tractor. So the heterogeneity of the cycles, agents and heterogeneity of the vehicles made a big difference. And more recently, we also extended this work to something called Dave, which is a data set we introduced, which is really diverse atomic visual elements for vulnerable road users. So vulnerability is a very big issue in autonomous driving because the big challenges are VRU, are bicyclists and human pedestrians. So how do you deal with vulnerable road users? Of course, easy cases, US highways or Western highways, there are no VRUs, but in urban environment, this becomes a very big issue. So this is a data set, people can do it. So I'll tell you a little bit more of what we have been doing. We're doing a lot of work on taking sensing and dealing with very complex indoor-outdoor scenes and the different challenges. Indoor scenes are okay, at least your buildings are mostly flat, nice floor. There could be obstacle like furniture and few moving people. But one big issue there is that you're dealing with humans. And as I said, it can get very crowded there. Secondly, you have like, for example, my own building at Maryland is full of glass. We love the building, but glass really makes a lot of sensors not work well. Lighting conditions change. So you're dealing with like lot of humans, and you're dealing with some challenging obstacles like, cloth, curtains, and something, the kind of thing you deal at home. Sometimes your AI gets confused, vision gets confused. Now, when you go to outdoor scenes, the outdoor world is not very flat. We saw in the very first talk, very nice talk from Toronto, that he was showing some really nice work. The terrain could be really uneven. And the previous talk, people like the work, how they were driving in the mud. It was really nice work. But how muddy is muddy? Is it little muddy, very muddy? If you have a big robot like a vehicle, you can go it. But if I have like a turtle bot here or a spot, I cannot do it. So dealing with the terrain and dealing with vegetation becomes very hard. And this is what we have been dealing with quite a bit. So this is examples of robot working inside with a crowd. Here the robot dealing with a glass, it collides. And here's like if you take your autonomous spot, sometimes vegetation comes, it get confused, this will happen. So these kinds of situations are very common, and this tells you we still have autonomous robots not there yet, and real world is too complex to really do it well. Now, especially at indoor scene, I've done a lot of prior work in crowd, many years ago, and dealing with very different crowds. We model crowds, and there's two kind of situation when there's very sparse crowd, where density is like less than 1 human per square meters, or when the density become one or two or more. Think of going to like a metro station or a soccer game. They're literally very difficult situation. So the question is, how do you deal with very dense crowds, avoid freezing, and also, give human social navigation or deal with groups? This is what we'll be dealing with. So I will not go too much technical details, but as I said, there's 50 years of work. There's a classical method based on, mobile motion planning, algebraic method, randomized methods, optimization-based methods, wonderful literature people have done. And of course, they give very good guarantees and interpretabilities, but somehow, they don't work well in dynamic scene. And also, a lot of the previous method assume a real representation of the physical world, like exact representation, which is not possible. It's changing all the time. So nowadays, robots have sensors. We have like in our work, we'll do cameras and LiDARs. We saw the first speaker talking about radar, wonderful. So there's been a lot of work on geometric methods and learning-based methods. Now, everything in green is the good things about what they can do. Everything in red is not good. Learning-based methods, are trained on simulation data. We have sim to real gap. Interpretability is not good. So as we look at these two methods, we say, what is working well, doesn't work well here. What if we combine the two? So we combine the two, hopefully take all the good green features and avoid the bad red features. And this is what we have been trying to do in our work quite a bit here. Second thing, we deal with dense crowds. And one observation people, psychologists and other sociologists have made, that if you go to a mall or real world scene airport, if you see in 60-70% of crowds in physical world are groups. There could be a couple, a family of 4, 3 friends. So a group means they're all kind of walking in similar pattern. They have similar goals, where they're heading to it. And the robot should not go between them. So this is something else we do perception quite well. So we did a lot of work. I will not skip the details on that. The paper's on the web. We first work on reinforcement learning, dealing with health dense crowd. This is the work in our building. This is about now 3-4 years old work. We took a turtle bot. We put a 2D LiDAR and a cameras. Now, when you leave a robot loose in your building, people do all kind of crazy things. So this is like, you see what people will do, just be mean and select robot, right? So this is what you have to do. Robot has to deal with all human situation. And of course, the robot is sensor at a height. And you see a laptop tied up because laptop was used for my reinforcement learning. We had a big simulator called Menge. We trained everything in Menge, and this is one place where Sim2L kind of sort of worked. It worked well. This was still having freezing problem. And this is a better solution, which again appeared about in 2022, 23 timeframe, where robot is really looking at how people are moving, anticipating their motion, and also moving in a manner that doesn't freezes. It's just like humans are very good at predicting other humans' motion and estimation prediction. And certainly we try to make sure that our robot sense are becoming very good so they can do it. So these are the solutions we propose where robots at least can show in quite dense environment there. Now, as I said, we work at Amazon. Amazon released its consumer robot. You can see a lot of reviews on, how people tested it. The consumer is a very hot problem. So you can see review in CNET where people say sometimes it works. People find corner cases where it doesn't work. So, a robot came and gets stuck in the kitchen with the furniture here. Or here was the example of, the lighting condition. You open the shutters and things go bad. So this is, corner cases come up, that there are too many cases where your sensing is not perfect. Exactly the same problem Waymo's been dealing for outdoor traffic. So one of the things we tried to do was we published this at ISR last year, and there was a paper before that, handling glass and shining objects, because you can't just use cameras, your computer vision will fail. So we proposed a new solution, and actually, we use some of the transparency of the glass. And in this case, actually, we did not use learning, we didn't have to go to learning all the time and not deal with GPU. We use an idea called multi-level intensity map, which is inspired by work on multi-level texture mapping computer graphics, and show it can work well. So this is one of our solutions, except in this case, use a LiDAR, which of course can be a little bit expensive for a consumer robot. But we tested this on all parts of our campus, and we're finding this can do a very good job of real-time detection of glass. So this is like if you have a LiDAR, it's a 360 LiDAR, it's invariant of the orientation of the glass with respect to sensing, and also can deal with lighting conditions. So this is the whole thing, that if you do some things well, that there definitely we can do robustly, deal with some environmental thing. And while machine learning is good, not everything has to go to machine learning. We can also do some things without using machine learning, using fundamental concepts, and this is being widely used now. So, and also when we work with Amazon, right? Amazon, while in the previous case, I used deep reinforcement learning, but Amazon people say, no, we can't afford a GPU for all this kind of computation. So we're working on what is called, a lot of MPC, which is a classic method. So in this case, we work with them. This work on my Senthil, working on very challenging situation of dealing with MPC extension, of dealing with T corridor MPC come up. So this is a method which was tested integrated with Astro Robot. Again, in interest of time, I'll just skip it. You see how this whole formulation works, control optimization, dealing with narrow passages right here. And as you go around here, this is examples of, previous method will get a little bit stuck. And we use a notion of what is called generalized collision probability, combine that with MPC, MPPCC, come with a modified method, and it can deal with very good challenging situations. So this is just with the camera sensors and our planner using modified MPC, and we can deal with difficult situation at home, because you need to make sure you deal with all this kind of problem. Here's an example of freezing problem, like a lot of times Astro will survive, will get frozen, but we can show no, it cannot get frozen, as we saw in the commercial demos. So this is some of the work on indoor scene. Let me take a few minutes of outdoor scenes. So here's the work on outdoor. As I told you, there are two big challenges. Your outdoor terrain is anything but smooth. As I said, it could be muddy, it could be vegetation, it could have rocks. Think of you going hiking. And secondly, one problem is vegetation. So here's our spot robot. We have a GPU for machine learning, a LiDAR, a camera, and it's making determination. You see vegetation. Is this vegetation soft like a grass, or this vegetation hard like a bush? Now, this is what comes down to what I call getting physical properties of physical world. Now, there's a lot of work in computer vision on dealing with object shape, object classification, but I still believe we don't have very good solution to figuring out physical properties. Humans can figure out quite well, and sometimes they use their hand sense with the semantic information, but computer vision today still lacks in dealing with physical properties, and that's a very big problem, especially with terrains or with vegetation right here. So, the kind of problem we deal with, like you could have collisions. So here the robot comes, it doesn't do a good classification, and you see it'll come in like a little bit trapped. And one idea is that you saw those autonomous cars, when you're unsure, you freeze, right? Okay, I'm not sure it'll freeze, but that's not a practical solution. And here you see the example of a tall vegetation. It gets stuck in the robot joints, it gets traps and all this stuff. So these are all the challenges come up with vegetation if you don't do it. And robots have to make sure to robustly deal with this problem. So we've been doing a lot of leasing method. We've published a whole bunch of papers in the last few years in ICRA, IROS, and RAL, other places. And one thing we're looking into is robot characteristics, and besides all the vision sensing, we look semantic segmentation, but we also measure interaction with the robot and the ground. The surface interaction tells a lot about the smooth surface or not surface like that. And similarly, for vegetation, we compare with references. So these are two ideas, we took them forward and quite a bit. This is one of the papers we published a few years ago on estimating surface traversability, Terrapin. It's also the code has been widely downloaded. A lot of people are using this Terrapin to figure out terrain traversability. And here's also a lot of work on different vegetation classification. This is sparse grass, dense grass, bush, and tree. So the question is, which of this situation can Turtlebot handle or a spot robot can handle? Turtlebot is much smaller. So you take a robot dynamics into account and make a decision which vegetation is traversable, which is not. That's what you will see here. So here's the example of, on the left, like we took the Boston Dynamics, this is a couple of years ago, their thing. So we found the inbuilt autonomy is not very good at handling vegetation. Here was one of our earlier solution where we can show, this is next to our campus, that we have all this vegetation and the robot can navigate quite effectively, dealing with grass and bushes, avoiding them or going through them, making a decision. So this was one of the first method where we can really deal with difficult vegetation and really, traverse in dense vegetation environment right here. Besides doing all the sensing, we're also looking for proprioception because humans rely a lot on, on the sense of touch, haptics. Unfortunately, robots don't have very good haptics, especially for locomotion. People are trying it for hands. So this is some work we've been looking into vibration analysis. And based on, stability of vibration, we can make classification of, besides this extraception, we figure out what do it. So on the right is a solution just showing computer vision perception. Here we do perception with some terrain traversal. So in this case, robot realizes on the left that the ground is kind of slippery or muddy. It slows down, changes its gait. So this is one way it can handle rough terrain because we humans, rely a lot of haptic feedback sense as we walk based on our shoes or something and affect our gait motion. Same thing we're doing here. So we're doing vibration analysis and showing that if you can do proprioception along with computer vision extraception, you can get much better navigation right here. There's more example of outdoor terrain. And this is again, bigger proprioception on the left, give us a lot of benefits in dealing with these complex situations. So this is the example of, again, how to deal with outdoor scenes and going like that. So this is an example a couple of years ago we did this work with Army people. You probably may not be able to see. This was navigation through a dense grass. Luckily, it was a sunny day, but the grass is 4 or 5 feet tall. And, we were so nervous. Our robot going inside, could it get stuck? We put a flag to make sure, my robot is still walking alive. It's kind of putting a flag. So you can see how it's doing it. Luckily, there were no big logs. And this was traversing through very dense grass and showing, yes, indeed, we can do this dense vegetation navigation if the vegetation is soft. But we don't know if prior vegetation is soft. And this is an example of, you'll see the same long-term vegetation. On the left is a camera. This is the camera in front of the ghost robot. You can see how it sees the ghost and do it. And this is a bird's eye view. So it detects the log and basically adjusts the gate and goes over it. So it's making real-time determination on where the vegetation is dense, where it is hard, soft, and trees, and literally, doing. So again, on the left, they're not totally synced. What you see from the camera on the front of the ghost, on the right, it's just somebody walking behind it with the iPhone camera, just observing. So you can see now we're getting to a stage indeed where we can do very long range navigation in complex terrain. And keep in mind, this is with a mobile robot. If you have a big vehicle, like we saw sometime, right, the dynamics are different. If you have a truck, of course, then you're dealing with torch bushes. So you take into account physical dynamics of the robot and the environmental constraints, and based on that, figure out what is do it or not. But to the best of our knowledge, this was among the first work which can deal with dense and complex vegetation with this legged platform. This is much easier for the vehicle, but much harder for this platform here. So recently, we also working a lot of cross gate, which is basically how do we gate modification. So this was a paper, we present IROS. We basically look at multimodal sensors. So you can see, depending on how the terrain characteristics change, robot dynamically adjusts its gates, locomotion, that how you change your goat motion. This will ghost for robot. It has 12 degrees of freedom. We change the ghost robot terrain automatically, slow, fast, step, so that it can navigate, see different kind of terrains like this. You can see muddy grass and sand, different kind of situation comes up. So this is very important how you adjust your locomotion to with that there. So that's one thing. Also, we've been using a lot of VLMs. VLM has a lot of benefits. It's not the perfect solution, but they are trained on internet scale data. So they offer a lot of, a lot of benefits for real world scene. It's not the complete solution, but they have a lot of benefits we can exploit. So this is the example of, you give example because you're in use language speech. You tell the robot, stay on sidewalk, follow the crosswalk, avoid the grass, and stop, stand, gesture. So now this is where the VLM benefits come up, it's following the instruction because you turn language instruction into the navigation behavior, and see on the right what it detects are like navigation region, like good and bad region. So the region that depends on saying stay on sidewalk and follow the crosswalk, so it gives high priority to sidewalk and low priority to the road saying and avoid the grass. So based on that we're doing it, and this was presented at ICRA just last month in Atlanta there. So this is what we're doing quite a bit, especially dealing with perception. And we think as VLM gets better, like Gemini and ChatGPT, use the knowledge, but you have to put some safeguards because VLM can also do hallucination and they don't do reasoning all the time. So this is all things of work going around there. And one other thing we are also working on is what Ikra presented, that we're also doing physically grounded. So most VLMs are, text, audio, and visual. How we can take physical interaction. As we get more physical data, people are doing foundation model that help this field. So I think I'm running out of time. I'll just skip up here and see if I have time for questions. I just want to summarize quite a few things. So we've been working on indoor-outdoor navigation. There are a lot of still challenges left. We showed you we can do indoor navigation to crowd, outdoor terrain. And if you're dealing with a consumer robot with edge hardware, we can do that. But there's still a lot of challenges. One challenge is we came up, besides dealing with environmental complexity, that let's do more sensing. We did cameras, lidars, IMU, proprioception. We look at polarization sensors. But as you put more sensors, it's good, they give you different complement information, but how to integrate them. And you have only limited compute, and dealing with different sensors and having the machine learning work is non-trivial. But overall, one of the challenge autonomy is, as Waymo has learned and other car companies, they're saying, you keep testing, collecting data because this is a very hard problem. And one other thing, as I said, if you integrate come ups here, one thing while computer vision is getting better and better, thanks to machine deep learning and LLM, VLM right now, but semantic understanding, and more recently, I would say acquiring physical properties. So I hope as robotics part of physical AI, that our focus will also work on acquiring the physical properties of the real world. What is hard? What is soft? Is it a tablecloth? Is it furniture comes up there? And of course, there are a lot of people doing VLM. There were a bunch of very good papers here. There was a paper we published a few years ago. It's going to appear in a conference, that while you deploy VLM, they also lead to safety mechanisms. So, all these solutions are benefits, but also cons. And our goal is to evaluate pros and cons and really figure out with that. So I'll just stop here. I want to thank my sponsors, and any feedback, time for question or feedback, I'll appreciate that. Thank you very much.
Thank you very much. So real quick, I see 3 people in the waiting room. Who is able to? Oh, thank you, Christian. Does anybody have questions for Dinesh? We got a couple minutes. We started late, so we've got about 4 or 5 minutes. Any questions? Are there any questions in the chat? All right, so Dinesh, I've got a question for you. So you seem to have been doing this kind of work in just about every environment. Are there any particularly interesting scenarios or interesting environments that you've encountered over your years of doing these kinds of things?
Oh, as I said, there are lots of them because we're doing outdoor terrains, right? And outdoor is way too complex. As I said, like all the video I showed, luckily we're on a nice sunny day, right? You're in California, nice sunny day. What if it rained? And what the ground is muddy? What if it snowed, right? Even Waymo is not trying to go, Waymo also driving in nice sunny cities. So I would say there's so many real world situations, and that we can't handle. So the outdoor navigation, full autonomy, especially with mobile robot, we still have a long way to go because real world is changing. The daylight, nighttime changes, rain changes, and we are might make a good progress, but we still have a long way to go.
Great, thank you. We've got another question. Can you guys pass this down? Yeah.
Okay. Is this working? Okay. Thanks for the talk. I really like the part where you were talking about grounding LLMs and VLMs in like physically grounding them. I think one of the challenges there, of course, is the lack of data. It's really hard to collect the right kind of data and then use that in an internet scale way. What kind of techniques are you seeing or are you excited about to actually physically ground LLMs or VLMs without as much data that we have for language or vision?
Yeah, that's a really excellent question with foundation models. And recently there's a lot of interest in foundation model. As I said, just Gemini made a new announcement, physical intelligence. So there, the question of data is very important because ChatGPT partially worked well. There were trillion words, and video works well because Google has 20 billion videos. So collecting real world data, some to tell you operations. So there's recently been a lot of interest in doing physics-based simulation. So, physical simulation getting much better, but of course, you can simulate a lot of human action, simulate material, but then you're still subject to sim to real gap. So the point you have raised is an excellent point that, to have physical grounding and even doing more physical work and even foundation model robot action, all these problems are really suffering from the data explosion. In fact, I know if some of you on ICRA, there was a very nice panel, and I think there were some estimates given. I think Ken Golo was showing the amount of data you would need for physical data. God knows how many years will it take. So a lot of people are doing simulation. There's one of former student of UMD. He's doing Genesis right now, physical simulation. Let's see how far they do it. But still keep in mind, we still have sim to real gap. So a lot of challenges for PhD students to solve.
Thanks.
All right. Thank you very much, Dinesh. Let's give one more round of applause.
And thanks everybody for your time. I apologize for not being here.